Hey, everybody. Woo! I haven't been to conferences in a while, and I mean, pandemic and everything. This conference reminds me of my first Scalar conference in 2016. It was in Norway. I got up on the stage and I was petrified because I could recognize people that I admired from the community, and my mind was screaming, "What in the world am I going to teach these people?" Kind of like that. So today, let me teach you about elements of JVM concurrency. And to set some expectations, we are going to talk about two topics. Mostly about the Java memory model, how Java deals with concurrency, but that's such a vast topic and I don't have the time for it, so I'm going to focus on some things that I think are important, synchronization and interruption. The goal being a confidence boost because I noticed that people are afraid of tackling concurrency issues in their code. And my wish for you would be to gain the confidence that my cat Zuzi here has in her everyday life. I mean, do you think she fears concurrency issues? No. And do you know what she does when she sees a bug? She goes hunting. And she gave me a lot of presents over the years, by the way. So concurrency is a semantic property of the program. You describe tasks as having independent execution, and then the runtime can choose to optimize it. Parallelism is a runtime property, an implementation detail that can optimize concurrent tasks. So parallelism is actual execution in parallel, and we have that on the JVM, and it's why things break, because we have shared memory concurrency, so to speak. So missing from these nice images here is the synchronization step, because if you chop vegetables at some point, you have to put them in the pot, right? So first, interruption, because it's a really important topic. Now, if you go back 10 years ago, Scala APIs weren't exposing a protocol for interruption, but now we have it, which is good, because Java also has a usable protocol of interruption, even if it's somewhat faulty, but it's usable, and we should use it, and we should describe APIs that provide a protocol for interruption. Because otherwise we end up with leaked resources or stalled progress. So how it works in Java? In Java, when we do interruption, we call thread interrupt because in Java we interrupt threads. And this sets an interrupted flag, a thread local value that we can check, and then we interrupt whatever it is that we are doing. It's a very cooperative process. What can also happen is to call methods that are interruption aware, such as thread sleep, which can detect interruption, and throw an interrupted exception. So this is how you usually see in Scala that methods are interruption aware. They throw an interrupted exception. That's not always the case, because with Project Loom, blocking I/O became interruptible, and you don't see interrupted exception on those methods necessarily. What you'll get there is some subtype of I/O exception, but never mind that. Now, Java interruption is usable, but error-prone. You must own the thread or do expensive synchronization, because in Java we work with thread pools, and when you're given a thread from a thread pool, it's not your thread, which means that if you call naively interrupt on that thread, you can interrupt some other task, right? Because the thread can be returned to the thread pool in the meantime. So you have to do synchronization there, and it's not easy because I've done it. So code can catch and ignore interruption, another problem. And Java code in the wild kind of does that, and if you did that in the past, please stop doing it. We need to have Java code being interruptible, right? And interruption is too cooperative. This compared, for example, with I/O in Cat's effect, which tries to be more preemptive, meaning that if you have a while true loop, you can't interrupt that, right? If it doesn't check the interruption flag, there's no way to interrupt it. The advice there would be to just use cats effect IO. And first of all, because it provides you builders for wrapping Java APIs correctly. I don't care what thread I'm using here because cats effect handles it. And the control you get, the precision you get with IO is unmatched. I mean, we are talking about direct style these days, but whatever direct style solution we are going to come up with, it's going to inherit Java's idiosyncrasies, right? Like being able to catch the interrupted exception and ignoring it, which happens in Kotlin, by the way. You can just catch cancellation exception and ignore it. So, which this can't happen in cats effect IO, for example, and it's preemptive, meaning that you can cancel flat map chains, right? So you've got extreme control when extreme compared with classic alternatives, right? You've got really good control when working with cats effect. And with Zio, the two implementations kind of converged on this topic. So, for this presentation, I propose that we implement a concurrent queue, right? Concurrent queue is like a really useful data structure we need to think about when doing communications between threads. You've got producers pushing messages to the consumers. Now, I wanted to talk in this presentation about monitor logs, but I don't have time for it because I've shortened my presentation, sorry. But, you know, useful sometimes, but usually avoided. So, the single most useful concurrency primitive for the Scala developer on top of the JVM is the atomic reference. That's because atomic references work really well in combination with immutable data structures. They only work with immutable data structures correctly due to visibility rules. And Scala is really, really great at describing immutable data structures. Now, doing the exercise, we can simply shove an immutable data structure inside the atomic reference. We have got an immutable queue in the standard library. We can use that. The general pattern of working with atomic references is as follows. You first read the current value from the atomic reference. You then create an updated version of that value. Immutable data structure, right? Only immutable data structures are allowed here, at least effectively immutable. And then, as a third step, we do a compare and set, which tries to store the updated value. This is an atomic operation, meaning that if multiple threads are battling for the same memory location, one of them will succeed, the others will fail. And if you receive a true as a result of this method, it means you succeeded, and then you can just do other productive stuff in return. Otherwise, you keep retrying, and this is a general pattern that you start seeing everywhere, including in the implementation of relational databases, which keep retrying the transaction until it succeeds. On the same model, right? Important here that when you retry transactions, and this is relevant for databases as well, the functions need to be pure, because if you have side effects in there, they'll get repeated, right? So the transaction keeps getting executed until it succeeds. Now, if we want to abstract this pattern, we need to think about pure state mutation, and this function signature should be fairly familiar to you, or if not, you can learn it right now. So this function signature is useful to model state evolution, right? So you've got a current state, like a state machine, and then you evolve it to a new state, and from that evolution, you also return a value that you may be able to use later, right? So this is also the signature of the state monad, but there are no monads here. So using Scala, technical difficulties. Wait. we are back. So, using Scala 3's nice syntax for extension methods, we can simply define a modify method that does the pattern that we talked about. It takes a function that evolves the state, evolves it, and remember this function needs to be pure. This is really important, right? We work with purity here. Now, the implementation on the producer side becomes really simple right now. We just do a modify on that, we receive that queue is being injected by the implementation, and then we call enqueue on it. That's a pure function, by the way. And for the return there, we are just return unit because we don't care. The consumer is slightly more interesting in this case because we want the consumer to block until there are events available. So what we are doing here is to describe a sleep and a retry. So we sleep, retry. This is like a polling action. We retry with a sleep in it until it succeeds. And this is a good strategy if you aren't in the mood for something else and it solves your problem, but we can do better. Right? So a really good strategy for dealing with all concurrency issues on the JVM is to think state machines. Even if you have an existing algorithm in your code that you need to somehow fix and untangle, right? Because concurrency is hard. You need to like draw it out on some drawboard, as a state machine in order to see if maybe you've got cases that you've missed. And Scala is really great at describing state machines because Scala is great at immutable data structures. So we can model a state machines, in this case with two states in it. One has events. We start with a has event state, and for receiving events as long as there aren't consumers available. And then we evolve to a has a consumer state when we receive a POP request with no events left. So when the queue is empty, we start collecting consumers that are semantically blocking, right? And then once we start receiving events again, the consumer queue is going to get depleted, and then we evolve in the has events state again. It's a simple state machine with two states. We either wait on events or we wait on consumers, and it's a really useful mental model. And we can model our immutable data structure using Scala's enumerations, two cases in it. We are using, again, Scala's queue, and for the consumer, what represents the consumer here is the callback. Callbacks are really generic, right? So when you wait for some asynchronous function to happen, the first thing you think of is a callback. We could have used a promise or a cat's effect deferred here. Doesn't matter. A callback is all we need. And here we are going to use like this kind of signature for evolving the state. We return an IO. Why do we return an IO here? Because the function has to be pure, and we need to suspend the side effect. And we've got side effects because we've got callbacks that we need to call. The callbacks being called are going to get suspended in IO. Now, we can model our pure functions. If we model pure functions, by the way, we can test them independently of the actual concurrency. The pure function, in this case, push event, takes an event and returns a state that either has the event in it, or it returns like the IO that calls the callback directly on that event, suspended because the function is to be pure. The implementation doesn't matter. This is an exercise for the viewer. Now, the POP event, again, we receive a callback, we receive a new state, and a suspended side effect. We might have events, in which case we call the callback in that suspended IO, or we might not have events, in which case we collect the callback in the internal queue. We also need a third function for registering the callback. This would be useful for interruption, because we don't want memory leaks and we want interruption to work. And now the implementation becomes really straightforward, and here I'm switching to cat's effect ref, which is basically what I showed you earlier, like it's an atomic reference underneath with some utilities. You shouldn't fear ref. It's pretty cool. And what happens here on push is that we simply call our pure function push event, which is going to, after concurrent set, the concurrent set underneath succeeded, that's going to spit out an IO unit, which represents the side effect, right? And that's going to be executed because we also flatten the IO, right? So in the context of IO, the side effect also gets evaluated. And then in POP, we are using the builder called async on IO. And we use pop event. IO async basically injects a callback that we can use. We register that in our internal queue, and we also return an IO unit like that yields some there. It's an IO unit that is going to be called by cat's effect in case of interruption. So interruption is nice and works and doesn't leak resources or stall progress, right? So the benefits of working with atomic references compared to other solutions like the synchronized block, right? Pure functions, immutable data structures that can be tested independently, cheap, really cheap sometimes, like you just shove immutable stuff in an atomic reference. It's asynchronous friendly because you can easily work with callbacks instead of blocking threads, right? Even if blocking threads is cheap, you'll find that blocking for some condition to happen is still difficult, right? Even with Project Loom, not to mention the gotchas that Project Loom itself has. Also, the algorithm that I just described is lock-free, which means it doesn't have schedule issues. It can have poor performance sometimes because threads end up contending on the same memory location. So you've got a bunch of threads, each battling on the same memory location, and that in some instances can yield poor performance. And in those rare instances when you need like extremely good performance for this communication, you need a specialized mutable data structures. This is where the, concurrent mutable data structures win, by the way, because they are able to distribute the contention between multiple memory locations. But usually, these are good enough and cheap to implement and easy and testable and so on. So, plot twist. When people think about synchronization, they think about atomicity, right? Those synchronized blocks. Is that instruction executing atomically or not? Well, a more general mental model that we can use is that synchronization is ordering, right? Forced ordering. And I'll explain what that means. But first, we are going to implement a naive queue implementation that has only one event in it. The producer blocks until the queue is empty. The consumer blocks until the queue is full. We are using two vars. We could have used just one var with an option in it, but that Boolean there makes things more clear, right? So that Boolean has event is used to signal the availability of the event. Now, the producer side waits until the queue is empty, and here we are using onSpin wait from Java 9, which tells the JVM that this thread is just burning resources, waiting on some condition to happen, maybe deprioritize this thread and do something else. It's useful to have when you're doing like well through like this, right? So it waits until the event was consumed, stores the event, and then signals its availability with has event equals true. This code is not thread safe, right? We are using just plain vars. No synchronization, no atomic references. But conceptually, right, order is important. Also, the consumer side, we wait until we have an event to consume, we process the event, we signal that we want another event with has event equals false. Not thread safe, but conceptually correct, right? The problem is that the JVM does reordering of instructions. And not only the JVM, but it's the JVM that we care about. The CPU can also reorder instructions, but the JVM reorders instructions in order to optimize memory access, because RAM access is really expensive, so which is why the architecture of CPUs these days is layered. So you've got processor registers, level 1 cache, level 2 cache, level 3 cache, and then RAM, and then solid-state drives, and then hard drives, right? So RAM access is expensive. The reordering happens because the JVM wants to like optimize cache, optimize the processor cache, right? It wants to avoid cache misses. And so what the memory model guarantees is that the order of execution is semantically correct only for the executing thread, meaning that from the point of view of the consumer here, the order is as if it was that in the source code. But that's not going to happen for other threads that observe what's happening. So you can have a reordered instruction like this. If has event equals false happens before the consumer has a chance to process the event, of course the producer can come in and overwrite that event with a new event, so you can end up with lost events. And similarly, on the producer side, the has event equals true can be reordered with event equals A, which means that the consumer could get a null value or an older event if they are executed concurrently. And if we push a value on the producer thread and we observe what happens on the consumer thread, with those two variables in memory, we can see like all possible combinations in there: false, null, false value, true, null. And the problem is that the probabilities of these outcomes is different. And it's different also between CPU architectures because the x86 architecture is better behaved than ARM, right? If you want to test concurrency bugs, you need to test on ARM because it's less well behaved. But I'm not talking about Apple processors because Apple made them respect more like the ordering of x86 architecture to make it easier to emulate. So ARMs, but not Apple. Anyway, the fix would be to introduce a volatile. And by the way, you don't usually do this in your everyday code. This is more like for optimizations for libraries, but it's good to see it working, right? And what a volatile is. A volatile is not really about flushing cache to memory as you get, you know. What is a volatile for? Well, it flushes memory, cache to memory. Well, no. I mean, it can do that. I'm not really sure actually, but what the volatile does is give you guarantees about ordering. So if has event equals false, if has event is a volatile, meaning reads and writes are volatile, it means that has event equals true cannot be reordered with the writes that happened before it. So has event here will be always the last thing that happens. But this is a warning. Reading and writing from has event in order to get these guarantees needs to happen in pairs. So the producer is also relevant. The actual guarantee is that once you see has event equals true, then it means that you also see the published event. And here on the consumer side, you get the guarantee that the reads that happen after the volatile read aren't reordered with the volatile read, right? So lines 6 and 8 aren't reordered. And a good question here would be if lines 8 and 9 would get reordered. So processing the event and has event equals false. I leave that as an exercise. But the short answer is that no, and if this were true, a lot of code would break, right? So there's a lot of similarity between reading and writing from and to a volatile with acquiring and releasing a lock. And I mean, a volatile is weaker. You can do less things with it. By the way, this is a single producer, single consumer queue. I forgot to mention it, and it actually works. If you have multiple producers and multiple consumers, well, it's not going to work, right? You need something stronger than a volatile. You need compare and set. But interestingly, there are a lot of similarities between volatiles and locks, right? So acquisition and release needs to happen on the same monitor, on the same lock. You heard that, right? And volatile reading and writing needs to happen on the same variable, otherwise the JVM doesn't give you nothing. If you think in terms of memory barriers, I mean, if you're like a C developer and you heard of memory barriers, writing to a volatile doesn't guarantee a memory barrier. No way, right? Because the JVM is smart for that. The JVM can eliminate volatile reads and writes via escape analysis, and it can also eliminate intrinsic locks just as well if it detects like single-threaded execution. And it's also completely unreliable, so like if you try to benchmark volatile reads and writes or synchronized codes, you're probably going to fail. Also, atomic references and monitor logs have basically the same visibility guarantees because they also have volatile semantics. I mean, if you were wondering why inside a synchronized block or why after doing like operations with atomic references, you get changes visible to other threads, well, because they also have volatile semantics. So anyway, the two takeaways here would be, oh, I thought I was in trouble. The two takeaways here would be that you need to think and use state machines, like in case you're not doing that, you end up in a world of pain. And pushing immutable data structures in atomic reference is a great way of doing that. And I felt pain when working with Java because finding a good library for immutable data structures in Java is challenging. And synchronization is ordering, which is an alternative mental model you can have when dealing and thinking about concurrency instead of the classic way of thinking of this operation is atomic. And yeah, you should meet concurrency issues with the confidence of Zuzi, my cat. That's her, by the way, trying to get inside. She's a sweetheart. Anyway, I think I was faster than anticipated.
And I love it.